thank you all you guys out there on the interwebs who are joining me today for this session on symmetrical components. I hope that I live up to the hype and make this interesting today. I know that we're both going to learn a lot. So before we get started, let me tell you a little bit about myself. So my name is Terrence Smith. I'm the Commercial Application Director for GE Grid Automation for the North American Commercial Region. So in that role, I lead the team of commercial application engineers. I joined GE in 2008, and prior to GE, I have worked at TVA and Mesa Associates. And today, we're going to talk about symmetrical components. But beyond that, what I really want to do when we think about this mathematical technique that we use, before we can do that, we need to review another mathematical technique, phasors, right? So we're going to review some phasors. Then we're going to review some symmetrical fault components. We're going to show how the sequence networks interact to create faults and how we can use the interaction of those networks and symmetrical components to calculate fault currents. And then we're going to take a couple of real-world examples. So I've got some oscillography at the end from an actual event, and we're going to look at that oscillography to see how it generates the fault-generated symmetrical components. And this will reinforce what we've done, or what we've gone through so far. And the other example I've got at the end is this conundrum that we face sometimes around polarization on transmission lines and what values we use to polarize and determine direction. And then as just a special treat, in addition to having 2 hours of symmetrical components, we're going to have a quiz at the end instead of a conclusion. So that'll help us reinforce some of the things that we've learned, and it'll give me some feedback on whether or not we learned anything. And don't worry, it will be an easy quiz. And if you pay attention, you'll probably ace it. So with that said, before we jump into the content, this is an interesting topic. It is a very heavily basic topic that all of us should understand as protection engineers. And I just wanted to point out to you guys that there is a lot of content that can help you in your growth as an engineer available on our resources page. So you can get to that content. This presentation will be available on demand on that page, as well as all of our previous Tech Talks. So you can get to that previous content through resources.gegridsolutions.com. And GE Grid Solutions is all one word. Okay, let's talk a little bit about phasors. Because before we can talk about this other mathematical concept, we need to briefly review this mathematical concept. So as we know, the rotating machine, the generator that generates electrical energy, as it rotates around, as it passes a pole, as the rotor passes a pole on the stator, the output, the voltage output of that rotating machine is a sinusoidal waveform, like the red waveform that you see in the middle of the screen. The problem there is that if I have a voltage that's a sinusoidal waveform there, and I need to apply that voltage through a resistance, or even worse than that would be an impedance that had some reactance to it that would actually shift the current that would flow through that from that voltage, I need a way to figure out and do that mathematics. It'd be really nice if I could, get closer to doing that in my head. Now, I could sort of, maybe if I was really smart and really a visual person, do that with that sinusoid. But most of us, including myself, really can't do that with that sinusoid. So we have to think of this in terms of a phasor. Now, what a phasor is we're going to take that sinusoidal waveform, and we're going to turn that into a vector. We're going to turn that into a magnitude and an angle. And that's what I show on the right side of that sinusoid. So we're going to take either do a Fourier transform of that sinusoid to get us a magnitude, or we could do an RMS transform and get the RMS quantity of that sinusoid, and that could be our magnitude for that vector. And then where that particular sinusoid crosses the zero axis at relative to other things, to other quantities on the power system, could be our angle, right? So that gives us a magnitude and an angle, and it lets us talk about this sinusoid as a vector, which is going to be very important for us to sort of do this mathematics. So for the purposes of our talk today, we'll do a little bit of vector math. Now, when we do vector math, there's lots of ways we can convert this into a rectangular coordinate, and then we could add it, subtract it, multiply it, all that good type stuff using the rules that we have for addition and numerical operators on a rectangular coordinate. But for our purposes today, to make this sort of simple, anytime that we do some vector math like this, we're basically going to superimpose one angle or one vector onto the other to come up with a resultant. So for example, if I want to add the phasors A1 and A2 that are shown on the left there, all I really have to do is superimpose A2 onto the end of A1 and draw a new vector between the origin and the new end of A2, which is superimposed on A1, which is this vector that we're showing here of A3. So you can see that this mathematical technique of creating vectors from that sinusoid is really handy as we apply that to we apply a voltage to a impedance and want to calculate the current through it, or if we want to do other analysis in the power system. So with that said, let's talk about symmetrical components. Right? So in a balanced three-phase system, like I'm showing on the screen right now, it's pretty easy to calculate things, right? So everything's balanced. This is a three-phase system. The magnitude of all three of the vectors are 3 units. They're equally displaced by 120 degrees. And if we were to apply this three-phase system here to a balanced three-phase delta-connected load, we could very easily calculate the current through that load. Or if we applied it to a balanced three-phase impedance, we can calculate the impedance through that, or excuse me, we can calculate the current through that impedance if these vectors that we show here are voltage. That would be easy to do because it's balanced. Unfortunately though, not all power systems are balanced. So imagine that if instead of this balanced three-phase system we have here, our three-phase system looked more like what I show on the right. And let's imagine that that's our voltages. So, I've got 9 units at 90 degrees. I've got maybe A phase at 3 units at just a little bit less than 0 degrees. What happens if I apply those voltages to a balanced three-phase impedance? What's the current through that? That is a much more difficult calculation than this balanced system. And the fascinating thing about this is that we really didn't have a really good way of analyzing this sort of system until 1917. So 1917, that's 100 years ago. That seems like a long time, but if you think about how long we were generating and transmitting electrical energy without the capability to analyze these unbalanced loads, and we didn't have computers to help us, and we didn't really even have calculators. And when I say we, I mean we as a species here. I'm not that old, guys. So when I say we in this context, I mean we as a species. We didn't have a way to, analyze that system. So it wasn't until 1917, Fortescue, a mathematician named Fortescue, developed this method of taking an in-phase system, in representing the number of phases in the system, and converting it to in discrete balanced systems. And using those in discrete balanced systems, we could analyze it because all three of those new systems were balanced. So in our context, it wasn't in, it was three, because we generate and transmit, and in many cases consume three-phase electrical energy. So since we've got a three-phase system, this mathematical technique can take that unbalanced system and turn it into three balanced systems. And the three balanced systems that we can turn this into, we describe as a positive sequence system, a zero sequence system, and a negative sequence system, right? The positive sequence system, or the positive sequence components, will always be present. If you ever do your calculations and your positive sequence components are zero while your other components are non-zero, you've made a gross error somewhere. If you're ever looking at metering quantities and your positive sequence quantities are zero and your other quantities are non-zero, then you've probably made a gross wiring error somewhere. But the positive sequence components are always present. They have an ABC counterclockwise phase sequence. All the phasors are equal, and they're equally displaced by 120 degrees. The zero sequence network, or the zero sequence components, they don't really have a sequence. They're all in phase, and they're all of equal magnitude. And the negative sequence components have an ACB, counterclockwise phasor sequence. So again, though, other than having a different phase sequence, it's similar to the positive sequence components because all the phasors will have equal magnitude and all the phasors will be equally displaced by 120 degrees. So that's what we're trying to arrive at. And the way that we will arrive there is through this mathematical technique. So there is a mathematical technique, and this is it. The formulas that I'm showing on the screen right now, to calculate a positive, a negative, and a zero sequence components. So this, I'm showing it for currents and voltages. Now the I subscript 1 is the positive sequence current. The I subscript 2 is the negative sequence current. And the I subscript 0 is a zero sequence current. And the same is true of the voltages to the right of that. And these are the formulas. We're taking 1/3 of the summation of the currents. Some of the currents, though, we will apply either the A operator or the A squared operator. What the A operator does, it is 1 at an angle of either 120 or 240. And basically all that does is that will shift your quantities that they are applied to by either 120 or 240 degrees. So what we're doing there on the positive sequence current, for example, is we're going to take A phase and we're going to sum that with B phase that is shifted by 120 degrees, shifted in a counterclockwise rotation. So it will, if it's a balanced system, it will be in phase with A phase. And then the A2 operator, and I'll show this in the next slide, what I mean by in phase. The A2 operator is going to shift it by 240 degrees. So if I take C phase, and if it's sitting at minus 240 degrees, and I shift that by 240 degrees, it's going to bring the C current, or the C voltage, in phase with A phase. And so that I can sum those together. So those are the equations. Make a mental note to memorize those equations. And once we have those equations, we can use those quantities to calculate things. The other thing that's going to be important is how we turn this into our phase quantities and convert them back from the sequence components back into our real world examples, right? So we can do that using the equations that I show down below. So for A phase, we can merely sum the positive, negative, and zero sequence components. Now, key point here is all of the math that I'm showing up here is vector mathematics. So I'm summing the vectors of I1, I2, I0 to get A phase. Same thing for B phase, except I'm going to shift I1 by 240 degrees with the A2 operator, the A squared operator. And I'm going to shift the negative sequence components by 120 degrees with the A operator for the B phase, and then I'm going to add that with I0. Very similar equation to C phase. So what this lets us do is this lets us take our phase quantities, voltage or current, and convert them into sequence quantities, positive, negative, and zero sequence. Once we've done our analysis, and once we've converted them to the sequence quantities, those sequence quantities represent a balanced system. And since they represent a balanced system, the mathematics becomes much easier. And then the mathematics to calculate current, loads, things like that. Once we calculated those quantities in our sequence components, we can then use the equations at the bottom to convert those back to our phase voltages. And that would be phase voltages that we would see, or phase voltages or phase currents that we would see on current transformers. They're going to be applied to our protective relays. If we're in a protective relay situation, we want to calculate fault currents so that we know what our fault currents are. They're going to be that the relay is going to see. But this goes even beyond relays, because I might want to calculate these fault currents for the purposes of determining if my breaker duty is going to be exceeded. If it's going to be exceeded, I might not be able to break the fault current that I have. So I can use this. This is one of the fundamental things that we should know as protection engineers, to be able to know what the fault current level is at a particular location in our power system. This will be important for for all of our protection, not just the relays, but the breakers as well, because we don't want to overduty those breakers. So, with that said, let's look at what this concept of the A operator does. So if I look at a balanced three-phase system, like we have at the top, right? The top of the half of the slide, that's a balanced three-phase system. So VA, if I'm going to sum VA plus the A operator times VB, and the A squared operator times VC, well, VB is sitting down there at minus 120 degrees. So if I shift it by 120 degrees, it becomes in phase with A. And VC is sitting up there at minus 240 degrees. So if I shift it by 240 degrees, it also is in phase with VA. When I sum those together, I get this new quantity that is 3V1. Remember, the equations that I showed took 1/3 of those summed quantities. So V1 there in this balanced system would equal those balanced phase voltages. Oh. Now, if I go back to this, I'm sorry. If I go back to this, if I took the B phase voltage and I shifted it by 240 degrees in that same counterclockwise location, in that same counterclockwise direction, it would be sitting up where VC is now. And if I took VC and I shifted it by 120 degrees, it would be sitting down where VB is now. And if I summed those three vectors, VA, VB, and VC, and VA and VC and VB shifted, that's going to sum to 0. And so that's why I would have 0 negative sequence voltage on this balanced network. Likewise, if I wanted to remember the equation to calculate the 0 sequence quantities was just the vector sum of those three, no shifting involved. And if I took VA and if I took VB and superimposed it on the end of VA, and then I took VC and superimposed it on the end of this new VB, those are all going to sum to 0. I'll be back to my origin where I started. So there's no 0 sequence quantities in this balanced system. Now, if we take a look at the bottom system, that's not a balanced system, right? Especially the currents. So the voltages look balanced, but the currents, they look like they're shifted a little bit, and they've not got equal magnitude. So if I look at the positive sequence components in the middle on the bottom, and I take IA, and then I shift IB by 120 degrees, it's in phase with IA. So those two are going to sum. And then I take IC and I shift it by 240 degrees, and it's going to be in phase with A phase. And so those three sum to the positive sequence quantities. Likewise with the negative and 0 sequence, let's look at the 0 sequence first on the far right. So if I look at the 0 sequence quantities, if I take IA, it's sitting there, down there at, minus 30 degrees or so, and I superimpose IC on the end of it, it brings me up to where the yellow vector starts, and that would be IB. And then the difference between the end of IB and where IA started is the 0 sequence quantity. And so actually it's 3I0, which is 3 times the 0 sequence current. And so that's how we calculate those negative and 0 sequence quantities. Now, typically, when I think about these quantities, if I have a balanced system, I'm going to have only positive sequence quantities. We know that. We know that from what we just did. Now, what I also sort of know is that anytime ground is involved, I have 0 sequence quantities also. I will always have positive sequence quantities, but if there's a ground fault involved some way, I'll also have 0 sequence quantities. The other piece to this is if I have ground involved or if I have phase-to-phase quantities involved, I have negative sequence. We're going to show why this is in a few more slides, but just keep that in mind. And in those few more slides, and why that comes to mind, is this concept of calculating fault currents with the sequence networks. So if I have an example power system, like this power system that I show right here, And this is sort of a simplified version of the power system. I've got a system and a source, and then and there's some system impedance, and I've got a line impedance in front of it. The reason I show this like this is because I want to talk about what I'm really interested in the context of these examples is what is the current at that CT location, right? So I'm really interested in the current at that CT location, which is I'm probably going to refer to in the coming slides as the current at the metering location, or at the relay location, or at the location we're calculating. So I may have a fault that's really far distant out on that transmission line, but what I'm really interested in is what that fault current creates at that metering location. So with that said, if I can have positive, negative, and zero sequence components of the power system, voltage and current, I can also have positive, negative, and zero sequence networks, right? And so what I'm showing over here on the right, this graphic here, what that really is that's the 3 sequence networks. And at the top, at the very top, where I show V1, that's the positive sequence network. Now, for that same power system that I just showed, and in the middle there, where I show V2, that's the negative sequence network. So there's the system impedance for the positive sequence network, system impedance for the negative sequence network, the line impedance for the positive sequence line for the positive sequence line, and there's the negative sequence impedance for the line. At the very bottom is where the V0 is shown. That is the zero sequence network. Now, these networks are discrete, right? Just like the individual components are discrete. Now, what I'm actually showing here is the way that these networks connect together for a phased ground fault, right? So these 3 networks have to connect together some way, right? And the way they connect together for a phased ground fault is they're in series, like I show them here. Now, there's a few things that I want to point out. The first thing that I want to point out is there's only one source here. That one source is the positive sequence network. So that is why, since the positive sequence network is the only place there's a source, that's why you always will have positive sequence quantities, right? The other piece of that is look at those voltages. When I look at those voltages, where is the voltage the highest in the positive sequence network? Well, the voltage is the highest on the positive sequence network when I get closer to the source. As I get closer to the source, I've got voltage drop through those impedances. So right across VS there is where my positive sequence quantities are the greatest, or my positive sequence voltage is the greatest. But look at my negative sequence and my zero sequence. What's the voltage greatest there? The voltage in the negative sequence network and the zero sequence network is created by the voltage drop across the network, which means the negative and the zero sequence quantities will be the greatest at the end of the network, right? So one way of thinking this is what generates negative and zero sequence currents. And what generates negative sequence currents, zero and negative sequence currents, is the interaction of these sequence networks. These sequence networks interact because of the fault. So we can say that negative and zero sequence currents are generated by the fault, which means, as a rule of thumb and an easy way to remember this, that those quantities will be the largest the closer to the fault we get, whereas that will be the exact opposite for the positive sequence quantities. The closer we get to the source, that's where those voltages will be the highest. And I should have said voltages throughout this discussion, because since these are in series, the negative sequence current equals a positive sequence current equals a zero sequence current. Well, how did I get this sequence network? How did this all come about? Well, if we look at how this all comes about, or how I knew to connect these sequence networks like this, I can actually derive it. Now, in most instances, you can go to a reference book and you can find how the sequence networks will interact for a particular fault type. But just for the sake of argument, let's look at how we would derive that. There's things that we know about a phase to ground fault, right? If we have a phase to ground fault, one of the things that we know is the faulted phase will have a lot of current on it. It will have fault current on it, so it's going to be very large. The unfaulted phases will be small, almost zero. So the question, so if we look at that and we calculate our sequence components, so IA is X, it's non-zero, right? IB and IC are small, so we're going to call them zero. So if I want to calculate I0, I'm going to sum 1/3 of IA, IB, and IC. In these equations that I show here for positive, negative, and zero sequence current, I've left off the 1/3 intentionally to simplify things, right? And we won't need it because we're just trying to derive the way these, we're not really interested in calculating the actual quantity. We're trying to derive the networks, right? So IA is non-zero, IC and IB are zero. If I sum the three together vectorially, IA and IB are zero. Excuse me, IB and IC are zero. IA equals X, which means I0 equals X. If I want to calculate I1, the next equation down is I1, the positive sequence current. And IA is X, IB is zero, so it doesn't matter what we shift it, it's still going to be zero. And IC is also zero, so it doesn't matter how we shift it, it's still zero. So I1 is equal to X. Same thing on the negative sequence quantities. I2 is going to be equal to X. So what we just derived is that I1 equals I2 equals I0. So all three quantities are the same. So the only way that we can connect those three networks such that the three components are equal, the I1, I2, and I0, the only way we can connect them is in series like this we show here, right? So what we know now is when we have a phase to ground fault, this is how our sequence networks are connected. And knowing that, if we all we need to really know now is the system impedances and the line impedances, or the source impedances, I'm calling it there. Once we know those, we can calculate the quantities. We can calculate the positive sequence current, we can calculate those voltages, and then we can turn those, using the equations we showed previously, we can turn those back into phase quantities. And that's what we're going to do in a few slides when we calculate some fault currents. But before we do that, let's look at at least one other example. On a balanced three-phase fault, we know that we don't have any negative sequence current, right? We know that we don't have any zero sequence current, so we only have I1 involved in that. But we also know on a phase-to-phase fault, on a phase-to-phase fault, we have quantities that I show here. We know that for a phase-to-phase fault where ground is not involved, that I0 is equal to 0, and that I1 is equal to negative I2. And the only way that we can connect these networks together is in the way that I show on the screen here. We connect them in this network like this, and now I1 is involved, the positive sequence network, the negative sequence network is involved, but as you can see, there's no connection to I0, so we won't be able to measure any negative sequence, or we won't be able to measure any zero sequence quantities. Okay, so there's a monkey wrench that we're going to throw into this. The monkey wrench is that transformers can affect the impedance of our sequence networks. And what I mean by that is we intentionally use transformers to block zero sequence quantities, right? So if we look at this transformer that I show on the right over here, it's a delta to Y transformer. The Y is grounded. It looks like it's solidly grounded. 50 MVA, 230 kV to 13 kV. This looks exactly like a utility distribution transformer. A transformer where we're stepping it down from 230 kV down to 13 kV. And we've wired that as delta on the 230 kV side. We've wired it as Y on the 13 kV side. And we've done that for a very specific purpose. The very specific purpose that we've done that for is that 13 kV distribution system is subject to a lot of ground faults. Ground faults from things like tree strikes, from squirrels, from birds reaching around the insulator. Squirrels would reach around the insulator too, but lots of faults, lots of ground faults there. So by grounding that Y and having that 13 kV side of that transformer wired in Y, what that does for us is that gives us plenty of ground fault current to sense those faults and operate for them. Trip the breaker so that the faults don't persist and do additional damage, or impose a public health risk or safety, public safety risk. So that ground there gives us the ability to have ground fault current that we can sense on that relay that we show there. The delta connection on the primary side, though, that's going to block that ground fault current, and we want that. And the reason we want that is because we don't want to have to coordinate on our 230 kV transmission system with our relaying down on the distribution system. We don't want to have to coordinate for those faults. We don't want to see all of those ground faults on our transmission system and affect the power quality of our transmission system. So that delta connection does something very specific for us. It allows us to block that zero sequence current. And so, what I show on the right there is several different networks. Several different networks and several different transformer connections, and what those zero sequence networks and the positive and negative sequence networks will look like to that transformer. And so what that means for us then is if we look at this is what the sequence, for a phase to ground fault, this is what the sequence networks would look like with that transformer. And so this is for a phase to ground fault on the 13 kV side at some distance down the line. Now our metering location is somewhere between the transformer impedance and the line impedance. That's where our relay was. So that's where our metering location is going to be, and that's where we're going to measure those sequence quantities. Now, what this does for us is this, like I said, it blocks those zero sequence quantities from the transmission system. If we were looking at this from the transmission system, and we were looking at if our metering location were in front of the transformer, right, on the 230 kV of that side of that transformer, what that means is we could meter that I1, we could meter that I2, but if that CT location is just above where the I0 is there on the primary of the transformer, there's no I0 flowing through that open section there. So we would not see zero sequence quantities on the primary of that transformer. The other thing it does for us is the zero sequence impedance of the system is not involved in our calculation for phase to ground fault. And that's important for something that we'll show in a slide or two. So, what are those sequence impedances? Well, for transmission and distribution lines, Z1, the positive sequence impedance, equals Z2. Z0, the zero sequence impedance, is always going to be different from Z1 because it is a loop impedance, right? It's going to be the conductor plus the ground. Now, this is one of the reasons that when you're setting a distance relay, some relay manufacturers will ask you for a K0 or a compensation factor. Some relays, like our L90 and D60, will ask you for the ratio of positive to zero sequence impedance. At either rate, the reason that we do that is because you're setting the reach of that distance element in positive sequence quantities. When you set a zero sequence quantity or a ground distance element, it needs to know what the ratio of that reach is. And so it's either using a K0 to calculate that, or we're giving that elsewhere as a setting. Now on transformers Z0, typically Z0 equals Z1 equals Z2. They're all the same. Except those transformers, depending on the connection and where your metering location is, Z0 may be infinity because of your location, your metering location, and the way you're interconnecting and transformer connection. So let's use this to calculate a fault current, right? So what I'm going to do is I'm going to take this power system here, and I'm going to calculate, and we're going to do this for a few different scenarios, a few different fault types. This first one's going to be a phase to ground fault, right? And it is in the substation, right? So we're going to assume that the impedance of the system is infinite. And this is an assumption that a lot of people make when they're calculating fault currents. It's good and it's bad, right? It's good in that it doesn't matter what happens in the transmission system or how it changes. You calculated the maximum fault current that you can see with that transformer on that bus, right? The other reason it's good is that the system impedance should be small relative to the impedance of the transformer. So even though your actual fault current might be a little less, if you then when you assume an infinite bus like this, it's not that much less, right? It's bad because you are calculating a quantity that is the maximum that it could ever be with that transformer, and which might make you overdo your breakers a little bit. But nonetheless, for our purpose, for our initial purposes here, let's assume this infinite bus. So here's my transformer. I've got 5% impedance on a 50 MVA base. So my positive, my negative, and my zero sequence impedance of that transformer are all 5% on that 50 MVA base. I'm going to connect my sequence networks like I show over on the right because I know this is a phase to ground fault because I'm calculating phase to ground fault current. So I know that from Ohm's law that current is equal to V divided by Z. So if I take 1 per unit of voltage and divide that by that 0.05 per unit of impedance, and I know that those three quantities are in series, the positive, negative, and zero sequence are in series, I can sum those together and on the bottom down there. When I take 1 over that, 3 times 0.05, that gives me 6.67 per unit. So my fault current is 6.67 per unit of the transformer base quantities. I'd really like to know what it is in the real world. So I'm going to take and calculate my I base, right? So my I base is going to be the transformer MVA divided by the square root of 3 times the kV of the transformer. So the base quantity of the transformer is 2,221 ounce. So I know that I1 equals I2 equals I0, right? And they're all equal to 6.667 times 2,221 ounce, which is 14.8 Ka for I1, I2, and I0. Now, what I need to do now is turn that into a phase component. So remember from that third or fourth slide that if I want to calculate a phase current, I can just sum I1 or positive sequence current, zero sequence current, and negative sequence current. So I get 44 Ka, 44,000 ounce for my available fault current on the secondary of that transformer. And one of the fascinating things here is what happens if I put 2 of these transformers in parallel, which you never do. And the reason you never do that is if we do this same calculation, since those 2 transformers in parallel, you've essentially halved your impedance. So instead of 6.6 per unit, my base or my fault current is 13.3 per unit. And I do the same mathematics I did previously, and I just doubled my available fault current by putting the 2 transformers in parallel, which is the reason you never put 2 transformers in parallel. You might be able to find a 50 Ka breaker, but you're not finding, it's going to be really difficult to find a 13 kV breaker that's rated for, 100 Ka or so. Going to be, I shouldn't say difficult, it's going to be a lot more expensive too. Okay, so let's do this same scenario and say what happens if we have a 3-phase fault. So instead of a phase to phase or a phase to ground fault, we're going to do this same scenario for a 3-phase fault. So in this case, it's a 3-phase fault. The negative and the zero sequence networks are not involved. So over on the right, the only network that is involved is the positive sequence network. So I'm going to do the same mathematics I did earlier. I'm going to take and find my fault current, which is going from the network that's on the right. I know that is 20 per unit because it's 1 per unit of the voltage divided by 0.05 per unit of the impedance, and the transformer impedance, and my current is going to be 20 per unit. My base quantity didn't change. It's still 2,221 ounce. So I'm going to multiply that 20 per unit times that 2,221 ounce, and my positive sequence current is 44 Ka. Now, I want to convert that to phase quantities. Phase quantities are going to be equal to the summation of the positive, the negative, and zero sequence quantities. Negative and zero sequence quantities are 0, so IA is equal to 44 Ka. So for this particular fault, the fault current is the same for this particular fault location, I should say. For this particular fault location, and the assumption that we have an infinite bus, the fault current is going to be the same for both the three-phase fault and the phase to ground fault. Now, as we move out, if the fault location changed, if it moved out into that distribution system, because Z0 is so much greater than Z1, as we moved out into that distribution system, we wouldn't have to move very far before the phase to ground fault current dropped off, and it was much less than the three-phase fault current for a particular location. This is only true at the substation bus or on the transformer secondary. But it's an important concept. It's something to be on the lookout for. We're going to do the same thing for a phase-to-phase fault, right? So let's assume a phase-to-phase fault on the transformer secondary right there at the bus. And again, we're going to connect the positive sequence network and the negative sequence networks as I show here. Zero sequence network is not involved. We know that because of the slide that I showed earlier. You can do the same calculation, but now the source DS is driving fault current through transformer impedance, the positive sequence transformer impedance, and the negative sequence transformer impedance. And so to find our fault current, we're going to sum those two impedances and to take the voltage per unit and divide that by those sum of those two impedances, which gives us a fault current of 10 per unit. Calculated previously that our base quantity was 2,221 amps. We can multiply by that by the 10, and that's 22 Ka. We sum the three networks together, and we're going to end up with the same 44 Ka. So let's back up and do this a little differently. Let's assume now that instead of having an infinite bus, we know what the capabilities are of our power system. And the way that our utility has given that to us is they've given that to us in the terms of an MVA. So they're saying that the available fault current is 215,000 MVA, right? They've also said that Z0 is going to be 3.5 times Z1. So the first thing we need to do is to, we know what our transformer impedances are. We've been messing with that. We calculated that on the last 3 slides or so. So we know what that is, right? That's 5% on a 50 MVA base. The system positive and negative sequence impedance is 1 per unit on a 215,000 MVA base, right? So we need to convert that from that 215,000 per unit base to our 50 MVA base, right? So the way we can do that is with the third equation there. So I'm going to take the ratio of 230 kV to 13 kV, right? I'm going to square that, and I'm going to multiply that by the ratio of the MVAs. And then I'm going to multiply that by 1 per unit to get it into per unit base of 50 MVA. So that is 0.0728 per unit for Z1 and Z2. I know what Z0 is because it's 3.5 times that. So now I know what all of my sequence impedances are, and I'm just solving a series network for I, for current. And so we can do that calculation there, and that current's going to be 3.38 per unit. Our base quantity hits that same 2,221 amps that we've been dealing with all along for a 50 MVA transformer. So we can multiply that current of 3.38 times that base quantity, and our fault current is 7.51 Ka. We sum all three of those, and our fault current for this phase to ground fault is 22.5 Ka. And so we can see there in this particular example that by ignoring the system impedance or assuming an infinite bus on the system impedance, that basically essentially doubled our fault current in this particular example. Won't always do that. In most instances, your transformer will be the limiting thing, but for my example today, it made it in half. So it's worth doing that if you can get the system capabilities. Let me point out one other thing before we move forward. The other thing that I really want to point out is imagine the same system if, remember that when we calculated the three-phase fault current, they were the same previously when we assumed the infinite bus. When we calculate using the system impedance, we had that to about 22.5 Ka. We're at about half of that. So since we're at about half of that, we can assume that the three-phase fault current would also be around this same quantity. But in this particular instance, one of the things that we need to point out is that this, at the substation bus, oftentimes if you know the system impedance and you're using the system impedance, the phase to ground fault current can be a little bit larger than the three-phase fault current. This is very important if you're doing a arc flash study, or even if you're calculating the fault current for the duty cycle to know the interrupting rating of the circuit breaker. That phase to ground fault current may be just a little bit larger. The reason it's a little bit larger is if we look at this, we previously calculated and showed that the two were the same. Now again, as you move out into that distribution system, fault current's going to drop down really fast for phase to ground fault current relative to the three-phase fault current. So after you move very far into the distribution system, hardly any distance in the distribution system at all, the three-phase fault current can be much larger. But at the substation, the system impedance, because of that transformer, that delta to Y conversion of the transformer, that system impedance isn't involved in the calculation for the zero sequence quantities, right? And because of that, that may make the ground fault current at the substation, at the transformer secondary terminals, larger than a three-phase fault current. So that's something to be aware of if you're doing an arc flash study. It's also something to be aware of if you're calculating the interrupting rating of your breakers and making sure that your breakers are capable of interrupting your fault current at the substation bus. Okay, let's talk about what this sort of looks like in the real world and what this looks like in an actual fault and a few other conundrums that we might face. So the fault that I'm about to show you is on this same sort of distribution system. This is a delta Y transformer. Again, so it's a distribution system. We've got something like 13.8 kV or 12.47 kV on that transformer secondary, which is on the right side, which is the side that is connected in a grounded Y. On the left side is a 230 kV transmission system that's connected in delta. Remember, we connect that in delta so we can block, we intentionally do this so that we can block those zero sequence quantities from our transmission system. We don't have to coordinate with them. The other tidbit of information that will be useful in this particular example is the F and the M that we show on the relay. The high side, 230 kV currents are connected to the F current bank on this particular relay. So when we look at this in the oscillography, it'll say F1, 2, and 3. That's A, B, and C phase. Likewise, the M is connected to the secondary. So when we look at that, it'll say, M1, 2, and 3. That's A, B, and C phase. So that'll be important. Now, the interesting thing about this particular fault that we're going to look at is that the fault is out. It's where we expect it to be. It's out on the distribution system. So it's a temporary fault. It's a temporary fault, and it's out on the distribution system. It might be a squirrel that got electrocuted and fell off. It might be a tree strike, but it looks like it's a fault that lasts 1, 2, 3 power system cycles. Now, the waveforms on the top, the red and the sort of orangish color that's on the top, that's the F1 and the F2 currents. That's IA and IB. So those currents are the currents that we are seeing on the transformer primary, right? If we look at the current that's a little bit larger down towards the bottom, that's the M2. That's the M2 current. Again, it's still in that sort of that orangish color, and it is the B phase current on the transformer secondary. So right off the bat, what we know is that this is a B phase to ground fault. So this is probably a squirrel or something that got on B phase. He got electrocuted in 3 cycles and fell off. The fault cleared, and life went on. Or it could have been that this was a successful. The distribution breaker may have cleared the fault, and then had a successful reclose at some time later. But in either way, this is a temporary fault, and we can see that it was on B phase. Now, there's a lot going on here that we just talked about. The first thing that's going on is that transformer is blocking zero sequence quantities. The only way it can block the zero sequence quantities is to have A and B phase quantities, to produce the fault current that we see on the single B phase. So the way that this transformer is wired, we know that B phase secondary current is going to be made up of a combination of the delta connection of A phase current and B phase current on the transformer primary. That's one of the things that we know. The other thing that would be interesting to see, we've already examined this fault pretty heavily. The other thing that would be interesting to see would be to see what the sequence components are on this particular fault. And as it turns out, I'm using InterVista UR setup to analyze this fault. So these are all screenshots from InterVista UR setup. And InterVista UR setup, you can configure it to calculate the sequence quantities. And if the circled quantities in the middle of the screen there are the pre-fault quantities, right? So the top circle is the transformer primary quantities, and the bottom circle's quantities are the transformer secondary. Now, the primary quantities, we see a lot of positive sequence current, and negative sequence and zero sequence are an order of magnitude or more lower than the positive sequence quantities. So that's what we expect. That's what we expect to see on that transformer primary. We expect to see some negative sequence quantities because the unbalance of the distribution system will manifest itself as negative sequence across that transformer. We'll still see that negative sequence quantities, but we shouldn't see any zero sequence quantities, and we don't because it's really small. Now, the second box that I have circled there, and this is pre-fault again, the second box there, what I expect to see there is I expect to see mostly positive sequence quantities. It is very different, unless you are serving nothing but three-phase loads in a distribution system like this, it is very difficult to perfectly balance your loads and all your single-phase loads, right? So since we're not going to be perfectly balanced, what I sort of expect to see there on my negative and my zero sequence quantities is I expect to see a little bit of that, and they should be equal, and that's what we see, right? So we're seeing 0.5 amps on the as a positive sequence quantities, and these are in secondary amps. 0.5 amps on the positive sequence, and negative and zero sequence are about 0.14 and 0.13. So they're about equal magnitude and significantly smaller, but not an order of magnitude smaller. So they're present. Again, this is pre-fault. Now, during the fault, here's my symmetrical components. During the fault, let me go through my build here this time. During the fault, F1, what I really expect to see there is I expect to see positive sequence quantities, right? I expect to see negative sequence quantities of equal magnitude, and I expect to see zero sequence quantities as zero. Zero sequence quantities as zero on the transformer primary, because that delta to Y transformer should block those zero sequence quantities. And that's what I see. I see 51.5 amps on I1, 51.2 on I2, and 0 on I0 on the transformer primary. On the transformer secondary, what I'm seeing is around 280 amps, and my positive, my negative, and my zero sequence quantities are all equal. So positive, equal in magnitude. Positive, negative, and zero sequence quantities are all equal. They're all around 280 amps, 270 amps to 280 amps. So they're equal magnitude. So let's take a look at, as a matter of review, let's take a look at why this is, right? So if I look at my currents on F1, which is on the transformer primary, what that means is my metering location, where I've actually got my CT at, is right above the 1 on the I1 in the sequence network, right above the 2 on the I2, and right above the 0 on the I0. So what I expect to see from that, if my metering location on the primary is right there, what I expect to see is I expect to see I1, I expect to see I2 equal to it, and I don't expect to see any I0. And that's what I see there. You know, I1 and I2 are equal magnitude. I0 which is negative sequence, or zero sequence quantities, excuse me, zero sequence quantities, it's 1, 2, 3, 4 orders of magnitude less than I1 and I2. So we call that zero. When you're 4 orders of magnitude less than your other quantities, that's a zero. So that's why. It's because of where our metering location is for those F1 currents. It is right there where that open is on the zero sequence network on the bottom. Right there above the I2 on the negative sequence, and right there above I1 on the positive sequence. Now let's look at this from the perspective of the other set of current inputs on M1. M1 is where our CTs are connected from our transformer secondary. And so that's going to be a different location. It's going to have a different look. And so what that's going to show is we expect our I0, our I2, and our I1, excuse me, to all be equal. And that's exactly what we see, because the networks are all connected in series, as I show here. And we're seeing that, it's around 270 to 280 amps for all 3 phases. The angle is a little bit different. The angle is a little bit different on the zero sequence network, and the magnitude is a little bit different because there is probably some inherent unbalance on the rest of the distribution system. That's of load that's still being fed during this fault. But essentially, they're the same quantities. So, let's look at, after having a look at that example, let's look at a conundrum that we can often face around transmission lines and how we polarize the transmission line. And this is, again, this is reinforcing some of the things that we just talked and we just learned about. In a transmission system, the holy grail of transmission protection is to tell the circuit breaker to trip in about a cycle or less, right? We want to trip as fast as we can. The problem with doing this with distance protection is, if I'm looking at the relay on the left, the dotted line looks like the reach that I can set that distance relay to. So the reach is the amount of the line that it will actually operate for. And so that dotted line, I can't go all the way to that breaker, because if I go all the way to that breaker, because of measurement errors, because of arc impedance, because of a lot of different things like that, I might overreach that breaker and actually trip for a fault on that bus that's at the relay on the right. Now, I won't do that, right? Because then I would lose coordination and I would end up over tripping. I trip equipment that I don't want to trip. So this leaves me a problem. I have to intentionally, for the zone 1 element that has no intentional time delay on it, I can't make it reach all the way to that breaker. So there's this end zone, right? There's an end zone that I show there where if I have a fault there, I can't trip as fast. So what I can do with a teleprotection scheme is I can set a teleprotection scheme like a permissive overreach transfer trip, a POT scheme, such that the zone 2 element overreaches. And by overreach, it'll reach into the adjacent bus. The zone 2 element I'm going to set with some time delay on its operation. Now I can set it with some time delay for its operation, but what I can do is I can use the pickup on that element. And what I can do is I can say, if I have a fault, in the on zone 1 on one relay, I can send a permissive signal from the other relay if the zone 2 element picks up. And what that does is that lets me trip fast for any fault on that line. And to give you a description of what that looks like, if I have a fault there in the end zone, this relay will see have fault there on the end zone. The relay on the right will see that fault, and he'll send a permissive signal to the relay on the left. Relay on the left, its zone 2 element that overreaches will see that fault. When it gets the signal, it will trip that breaker, and I can trip fast. Now, for ground faults, I have a particular problem. And my particular problem that I have for ground faults is that when I have a ground fault, will very likely have a arc impedance or some fault resistance associated with the ground fault. Now, what I show here is the characteristic angle of a distance element. So the orangish pumpkin colored circle is the operate region of the distance element in the relay. The line ZL is the reach of the element inside the relay. So if I have a fault along that reach, along that line, I will be inside of that pumpkin colored circle, and I'd operate. I'd trip the breaker. Now, the problem with ground faults is that my fault impedance, because of the impedance of the load, or impedance of the arc, or the impedance of the fault, that fault impedance can move the apparent impedance outside of the operate circle of the distance characteristic. So you can imagine if I look at that arc impedance of the no load fault resistance, the resultant impedance is if I draw a line from the origin to the end of that line, it's well outside of the characteristic of that distance element. So that causes me some problems. I'm not going to operate for that. Now, there's a couple of things that utilities can do. One of the things that they could do for the transmission lines, they could use a different characteristic, a quadrilateral characteristic, rather than this sort of round Moe circle that I used there. That causes some other problems. What most utilities will do is they will use a ground directional element. They will use a ground directional element to sense those ground faults, and if both of the relays sense the ground direction, the ground fault in the same direction, they can operate with the permissive overreach transfer trip scheme and operate fairly fast. The conundrum that we get, though, is remember what generates the voltages, right? Our positive sequence voltage is generated by the source in that positive sequence network. That means that our positive sequence voltage is going to be the largest at the source. And then our negative sequence quantities are going to be the largest at the fault location. Our zero sequence quantities are going to be the largest at the fault location. So what that means to us, is that we might have a problem if our impedance in front of the relaying location is very large compared to the impedance behind the relay location, because we need to use a polarizing quantity to determine the direction of the fault. And that polarizing quantity can be either V0 or V2 for a phased ground fault. And if we have a large impedance in front of us and a small impedance behind us, then we may not have a large enough negative sequence or zero sequence voltage to actually polarize our ground directional overcurrent. And so that's a problem in the power system, right? And again, let's look at this to recognize why our V2 is larger as we get closer to the fault location, and our V0 is larger as we get closer to the fault location, and our V1 is largest when we're at the source. So remember, V1 is going to be equal to the voltage produced by that source there that we show, Vs, minus the voltage drop across that system impedance, Zs1, right? The positive sequence system impedance. There's not a source in the negative or the zero sequence networks. The only source that it has is the source that's in the positive sequence network and the interconnection of these three networks. And that interconnection is caused by the fault. So the voltage that we see at V2 there is actually equal to the negative sequence voltage times that source negative sequence impedance, because that's basically the voltage rise across that network, across that negative sequence network. So that means where we interconnect between V2 and or where we connect between the negative sequence network and the zero sequence network is at the fault location. It's also where our voltages will be the highest. That means if we're really close to a source and our source impedance is not particularly, is particularly strong, we may not have enough voltage there to operate. So one of the mechanisms that we can do that a solution to that can be to use dual polarization. So dual polarization, the relay can decide to either use V0 or the actual current that's flowing through the relay. Okay. So I promised a quiz at the end of this, and I intend to keep that promise. So get ready. We're going to have this quiz, and let's say our problem number one, the positive and negative sequence currents are equal and opposite. So our positive and negative sequence currents are equal and opposite. So I'm going to say their magnitude is equal, but their vectors are in opposite directions. Zero sequence quantities are a different value. Positive, negative, and zero sequence voltages are equal. So the positive, negative, and zero sequence voltages are equal. Now, here is a list of different fault types, right? So here's a list of different fault types. What type of fault? Now, so the way you read this is at the very top is how the phases are connected, right? So, for example, the one over on the far left is a three-phase fault. The far left and the top is a three-phase fault. And then just below that are how those sequence networks are connected. And you can see for that three-phase fault, the sequence networks are not connected. So looking at this, what do you think the fault type is? So take a look at this and get ready, because I'm going to proceed to the question, to the poll question. So here's your questions. What is the correct response to problem one? Is it a three-phase fault, phase-to-phase fault, or a phase-to-ground fault, or a phase-to-ground fault? A phase-to-phase to ground fault or a phase-to-ground fault? So I'll give you a moment or two to answer, to submit your answers, and then we'll look at the results and we'll see how you guys did. And let's just to go back and review. Oh, I don't think we can do that now that we've gone to there. All right, let's check out your answers, guys. Okay, the overwhelming majority, well, I would say overwhelming majority, but most people, 40.2%, 40.2% said it was a phase-to-phase to ground fault. So let's see, 40, 80, yeah, less than 10% refused to vote. That's great. Let's try to get it 100% next time, but most people said it's a phase-to-phase to ground fault. Let's take a look at the actual answer, right? So if we actually look at this, yes, it was a phase-to-phase to ground fault. It was actually this one, and there was some impedance there, which is why we saw some of the quantities a little bit differently. Okay, let's go on to the next quiz question. The next quiz question are positive and negative sequence currents are equal and opposite. So they're equal magnitude and opposite directions. And there's zero sequence current. So based on that, so positive and negative sequence currents are equal and opposite, and no zero sequence current. So here's a look at the networks. Here's a look at the different networks. You shouldn't need to look at this because we went through this. And this is not one we derived, but you ought to remember this one. And so our choices are a three-phase fault, phase-to-phase fault, or a phase-to-phase to ground fault, or a phase-to-ground fault. So please submit your answers. Let's see if we can get to 100% this time. Maybe if I kill a little bit more time, those that aren't voting will feel socially shamed into voting. Hard to socially shame anybody, though, without in a virtual world. Okay, let's take a look at the poll results. A phase-to-phase fault. 70.5% voted for a phase-to-phase fault. 20.9% said it was a three-phase fault. And 7.6% said a phase-to-ground fault. And 1% said it was a phase-to-phase to ground fault. So that means only a little less than 30% of you need to go back and rewatch this, right? But the overwhelming majority, 70%, got this right. It is, in fact, a phase-to-phase fault. Now let's take a look at that. The reason it's a phase-to-phase fault is we'll take a look at that. For a phase-to-phase fault, the positive sequence network and the negative sequence network are connected together. The zero sequence network is not connected, so we won't see any zero sequence quantities. We'll only see positive sequence quantities and negative sequence quantities, and they should be equal. And because they're connected in parallel like this, they should be equal, but in opposite directions. Okay. One of the questions I've got here is, how do I determine negative and zero sequence values when I'm only given positive sequence quantities? Do you have any rules of thumb? That's an interesting question. It's an interesting question. It's one of these questions that we could talk about philosophically. And the reason that we could talk about it philosophically is because what you're trying to do, what you're asking to do, is to solve a multivariable problem with only one variable. The reason I say it's philosophical is that most of the time when I mess up in life, I'm trying to solve a multivariable problem by only addressing one variable. That is a great way to mess up philosophically. So you cannot solve a multivariable problem that has 3 different variables with only one variable. Now, there's some exceptions there, right? There's some exceptions. The exceptions are, if you know a little bit more information, you can start to make some intelligent assumptions. Now, as we think about the way that we can get information as an engineer, there's really 3 ways that we can get information as an engineer. The best way to get information as an engineer is to calculate things, right? And the reason I say that's the best way is because when we calculate things as an engineer, we don't feel like we have squandered our engineering education, right? We put that engineering education to use. So I always say that's the best way. The actual best way is to test things and to get real world quantities. The third way that we can get information as an engineer, which is the absolute worst way, is to guess, right? We don't want to guess. We want to guess as seldom as possible. But in this case, since we're trying to solve a 3-variable problem with a single variable, we're going to have to make some, if we want to do this, we're going to have to make some intelligent assumptions. So there are some things that we can do. One of the things that we can do is, if we know the fault type, right? If we know it's a phase to ground fault and we're given the positive sequence current, we've also been given the negative and the 0 sequence current, right? Because those 3 are in phase. If we know the fault type, we've probably got enough information to calculate some of those other quantities. Because if we know the the positive sequence and it's a phase to ground or phase to phase fault, we've also been given the fault, the negative sequence. We've also been given the 0 sequence, because the 0 sequence is 0. The negative sequence is equal to the positive sequence for a phase to phase fault. So for fault currents, if we know the fault type and we're just given, the positive sequence quantities, then we could probably, in most instances, calculate negative and 0 sequence. For voltages, if we're just given like the positive sequence voltage, if we know the fault type, we can probably calculate the negative sequence voltage, because it's probably going to be a similar quantity, but we probably can't, because it's going to be their voltage drops and voltage rises. So for the most part, if we use the interconnection and the fault type for currents, we can make some intelligent statements. If we don't know the fault type and we're just given the positive sequence quantity, we cannot make any intelligent statements about the negative or 0 sequence. So I guess the long answer is, or the shorter answer might be, it depends. Depends on what other information we know. Here's another question. Here's a great question. How can ground fault current be larger than 3-phase fault current? So this goes back to the example that I gave, where we were given the system impedance and we calculated the system impedance. So assuming an infinite bus, remember, the phase to ground fault current, 3-phase fault current were the same quantity. They were the same, given an infinite bus for a fault on the transformer secondary. If we don't have an infinite bus, we actually put the system impedance into that calculation, because the phase to ground fault, because we're basically blocking that 0 sequence impedance of the source from the calculation because of the transformer connection. Since that's been blocked there, we won't see that impedance in our calculation, and that can make phase to ground fault current slightly larger at the bus than the three-phase fault current. And again, as we move out into that distribution system that we were describing, as we were moving out into that distribution system we were describing, the fault current drops off very quickly. Okay. Okay. What is the maximum value that you would expect negative sequence or zero sequence current or voltage to be? It's a great question. What's the maximum value that we would expect negative sequence or zero sequence quantities to be? So one of the things that we know when we talk about current, we never expect to see the negative, we never expect to see the negative or the zero sequence quantities larger than the positive sequence quantities. If we're looking at a meter and we see negative sequence current is larger than the positive sequence current, and we're looking at that meter has some wiring errors on it. Or maybe it's possible a setting error, but more than likely it's got some wiring errors on it. Or a relay. Relay would do the same thing. So we would never expect the currents, negative zero sequence currents, to be larger than the positive sequence quantities. As far as the voltages go, if we're in the steady state, if we're in non-fault conditions, what we would expect to see on voltages is we expect, and this is true of currents as well, if we're in steady state conditions, we expect to see very little negative sequence or zero sequence current. The only negative sequence or zero sequence current that we should see in the steady state non-fault conditions would be the current associated with unbalanced loads, which if we've done our work right, we balance loads as much as we can, that should be very small. Likewise, since our negative sequence, zero sequence currents should be small, our negative sequence and zero sequence voltages should be very small also. So we would never expect, in the steady state, those quantities to be anywhere near the positive sequence quantities. And just because of the role that I've filled inside of GE as an application engineer, I know what a lot of wiring errors look like. So for example, if we swap the phases, right? So we wire B phase to A, C phase to B, and A phase to A on input on the relay, our negative sequence quantities would be 100%, and our positive sequence quantities would be 0, right? So if we see that, we know we've got a wiring error, right? Another example of that is if we swap one of the phases. So one of the phases, instead of wiring to polarity on the relay or the meter, we've wired to non-polarity. Then we're going to see the negative sequence quantity be about 33% of what we would expect the positive sequence quantities to be. And positive sequence quantities are going to be about 66% of what they should be under normal conditions. So, if our normal voltage is 12 kV, we'd expect, our positive sequence quantities to be, 2/3 of that, 66% of that, something around 7 kV. If we have swapped one of the phases. So, if we're up around, we're up over, 10, 15% in the steady state for any of our sequence quantities, we're over those quantities, then we've probably got a wiring. If we're looking at a meter, we're probably looking at a wiring error. If we're doing a calculation in the steady state, we've probably messed up our calculation. And certainly, if it can never be greater than the positive sequence voltage and current. Okay, that's a repeat question. What are the impacts of the 61850 standard on the use and interaction of symmetrical components and how they interact? Well, 61850 is a standard. It's an IEC standard. IEC 61850 is an IEC standard. And there are a lot of things that are defined in that standard, right? Things like communication protocols, engineering tools, logical nodes, things like that. The positive or the sequence symmetrical components, it's a mathematical technique, right? So the two are somewhat divorced from each other. The way that they are somewhat married is that the IEC standard does have logical nodes for metering quantities for those symmetrical components. So there are logical nodes for MMXUs for negative sequence, positive sequence, zero sequence, voltage, and current. And likewise, there's logical nodes that the standards defines for protective elements that would operate from those sequence quantities for protection elements. So like a negative sequence overcurrent or a zero sequence overcurrent, they're going to operate from those quantities, and there are logical nodes that define those quantities. And I think that's the real question you were asking or trying to ask. Modeling the power system impact of reactive installations, cap banks, shunt reactors, etc. So when you're modeling, capacitor banks and shunt reactors and things like that, those are reactive loads. They don't really change. They don't really change the symmetrical components and how the sequence networks interact. The only thing that they would change is, those impedances would be mainly reactive. So they'd be at 90 degrees rather than some other angle. This is one I don't really know the answer to, but it's such an interesting question, I'm going to read it anyway. In a two-phase system, traction rail, should the non-zero component be described as positive or negative? And the reason I find this interesting is that when we typically think about Fortescue's equations, these equations that calculate symmetrical components, we think about them as three-phase, right? Because our power systems typically are three-phase. But the actual paper that Fortescue wrote in 1917, it was about turning an in-phase unbalanced power system into N, N being the number of phases, into N equal phases. And so that would apply to a two-phase system, or if you had, a multi-phase that was different than three, it would apply there. So in that instance, I would need to go back and I would need to read Fortescue's original work to see whether that should be positive or negative, or even if it should have a name like that. Here's a great question. Which books do you use as a reference? So one of the best books that you can get to as a reference is a book that is in the public domain, and GE has made this available to you free of charge in the public domain. And that book is The Art and Science of Protective Relaying. So I don't have the link, on the top of my head right now, but if you do a Google search on GE Art and Science of Protective Relaying, you can find that book as it's on our website as a PDF, right? And that's a great book, and since it's in the public domain, that's where I'd start. Again, like I said at the beginning of this, there are a lot of resources. That particular book is on our website, GE Grid Solutions, but you can get to a lot of a lot of content. If you're interested in content like this, training videos, you can get to those at resources.gegridsolutions.com. A couple of other books that I use a book called Applied Protective Relaying. It's probably the best for symmetrical components. It was written by Westinghouse, and I use Blackburn's Protective Relaying Principles and Practices. Sometimes I'm only given the available three-phase fault current, and my software requires line to ground fault values to be inputted. If I guess at the line to ground current, I can get a zero sequence impedance negative error. Can I assume negative sequence impedance, positive sequence impedance calculated from three-phase fault current and determine what the range of line to ground fault current would be? Well, as you move out into the system, or depending on where you're at in the system, you know that your line to ground fault current is going to be lower than three-phase in most instances. The one exception that I really wanted to point out was at the substation. At the substation are the transformer secondary terminals. That's the one exception to that. But in most instances, it's going to be less. Again, like I said, I don't really like to make assumptions and guess at numbers like that because it'll affect the rest of your calculations. Okay. For phase to ground fault on the delta side of that transformer I'm sending, what function on the relay installed on the Y earth side would detect the fault? So for a phase to ground fault current on the delta side of the transformer we were looking at, that was a distribution transformer that did not have a source on the distribution side. But if I did want to sense a fault on that delta side, there's things I could do, and there's things that we would do. So that same, something similar to that might be a generating station, a GSU. A GSU transformer is going to have on the generator side and Y connected on the transmission side, for almost the same reasons that to block zero sequence current from the generator. And so in that case, we want to trip for fault currents on that delta side of the transformer. And so typically there we would use a distance element that overreaches and reaches through the transformer from the generator. Relay will only see the actual current. How does the relay work in the old electromechanical relay and the difference from the new IED? Well, that's an interesting question. You're right. What you connect to the relay, you're not connecting. You're connecting those three CTs. You're not connecting sequence networks. The relay will use those same equations that we use in that third or fourth slide. It will use those same equations to calculate those sequence components. It can build negative sequence overcurrents, things like that. With an electromechanical relay, you basically had to wire and build filters. So you can a zero sequence or a ground current filter, and you can do that by merely summing the three CTs together with wiring, and that's how you wired your currents for a ground overcurrent, right? And so really you're wiring a ground overcurrent, but really you were building a zero sequence current filter. And you were applying 3I0 to that electromechanical relay. Similar things with negative sequence. It's a little bit more complicated than the zero sequence, where you just got to sum the three. Basically what you're doing is you're wiring the three CTs into parallel and taking that parallel connection out to the ground relay, and that's how you would sum them and build that zero sequence. You clarify the application of 3V0 ground fault detection scheme. in question. And I think what you're asking there is, for an ungrounded system, can you clarify the 3V0 ground fault scheme? And basically what you can do for an ungrounded system is you can connect a set of VTs in what I would call a open delta, which is a different connection than a broken delta. And what a broken delta connection is I take 3 VTs in delta, but where I'm making up my last connection between, you know, where I'm closing up the delta, I run those 2 wires out to a device, and those 2 wires on that broken delta will have 0 sequence voltage on it. And if you have it's not a ground fault because it's an ungrounded system. If you have an ungrounded system and one of your phases becomes grounded, you will be able to see some on that broken delta voltage, or on that broken delta set of VTs. And so you can use that system to detect a grounded phase on an ungrounded system. I wish I had slides on that. That's something that's hard to describe in an answer. So you have my apologies. It'd be easier to describe with pictures, or if I could draw. Instead of protecting line with a distance relay, why not use the line differential protection, or is cost way too high for this type of system? Accurate statement. A better mechanism for protecting transmission systems is a line current differential, right? The reason that we don't have line current differentials on every single transmission line out there is because we've only recently, say we here, I'm referring to us as a species, we've only recently had our system line differential, you know, phaselets and quantities, lines that were built, you know, in the time frame when communications didn't exist for that, or we didn't have the communications that exist for that. So a lot of those transmission lines that are out there don't have those communications. In a pot scheme, you're not sending a lot of information like you are with a line current differential. You're just sending a permissive signal, so it's a bit. Whereas with a line current differential, you're having to send stuff, you know, every 8 milliseconds, and you're having to send phaselets or phasor magnitudes and angles for each of the, and so it's a higher bandwidth requirement, so more communications requirement. So that's why you don't find it on every one, is because not every one, a lot of the ones that are out there in the wild, they don't have the communications, and some of them don't. Some newer lines, you know, the communications either isn't there or it's not being installed. But what we see is that are built today, line current differential is such a better mechanism to protect. I know that I am at the capabilities of my voice, and my voice is starting to run out after 2 hours here. So I will turn the floor back over to Tassie and let her give you her concluding remarks.
Thank you, Terry, and thank you everyone for attending. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful rest of your day. Thank you.